Hello, welcome to the session Lipids, Compartments and Early Metabolism, ISO 2021. My name is KepaRuizMirazo from the University of the Basque Country. I suppose that quite a few of you know me already, but just in case. This is a kind of a strange situation in the sense that I'm pre-recording my talk today, the entrance to this session, in which I will also introduce the other speakers. And it's a bit weird to be speaking just to the screen and kind of overcome this psychological barrier. I will fool myself somehow and say, okay, it's everybody who is interested in origin, all the community of origin of life people are there for the first time in my life. I'm speaking to all of them, not just to a reduced audience. And I will try to give the best to share some ideas and results with you. And I hope that they are of interest. The first thing I want to say is thank you to Uli and Jim and all the people in the scientific community for the opportunity to speak here. And also for gathering us, for putting all of us together, even if it's in this strange situation in which we still have to do it online and not face to face. And also strange in the sense that these 2 years for me have been very, very hard. And I'm very glad to catch up with all of you, even if it's under these circumstances. So, let's get going. I'm going to share my screen and start with the actual presentation. Let's see. Okay, so as I said, I am the one in charge of opening the session, lipids, compartments, and early metabolism. This is a session in which we have a great lineup of speakers, and I will introduce briefly what each of them will speak about, but then you will have time to go into more details with them. I apologize because I'm not gonna be there. I'm not gonna be involved in the discussions. Unfortunately, it's the session, or the time of the session is a bit out of my capacities these days. I'm getting old, and waking up at 3:30 or 4 a.m. It's a bit too much for me these days. But I am available through email or even for encounters, online encounters, for anyone who is interested in the stuff that I speak about or whatever. I'm available. So please do write to me or propose to me meetings online for discussing whatever you want. So after me, the first speaker will be Nita Sahai, who will speak about the transition between this approach that she has about the transition between geochemistry and biogeochemistry. I would say that all these 4 speakers that will come after me, they are quite well together in the sense that they do take a kind of a systems approach. They are taking into account, for example, compartments or mixtures, complex mixtures of components and how they get organized. And therefore, all of them share that approach in which they are concerned about, let's say, the organization of a bunch of molecules that could be prebiotically relevant or relevant for the origins of biological systems. And Nita will start nicely from connecting, let's say, geochemistry with biochemistry or biogeochemistry, and pushing in that direction. And then we will have Greg Springsteen speaking about the work that he's been doing in collaboration with Ram Krishnamurthy, visiting the neighborhood of the TCA cycle. I think it's a very clever approach in the sense that they're not going straight to or mimic directly the TCA cycle, but exploring the neighborhood, the chemical neighborhood, and that gives more flexibility, maybe I think it's clever for origins of life, from an origins of life perspective, because it gives room for evolution to happen also, for catalysts to actually drive from that neighborhood to the actual metabolic pathway, and this kind of approach is very interesting. We will hear from him soon. Then we have Neil Devarai, who will speak about the formation of compartments, vesicles, and cell-like membranes, but coupled with the actual synthesis of it, which is something that is also very important, and I will highlight during my talk how important it is to actually have both processes of synthesis and then self-assembly of supramolecular structures in the system, to actually make progress in this direction, systems chemistry and systems biology. And then last but not least, we will have Tony Gia. I don't know exactly how he pronounces his name, but as a representative of let's say, a subgroup of the community of origins of life that is pushing hard for a lot of momentum these days for coacervates as compartments. This also comes together with a lot of work being done in biology, in cell physiology, which phase transitions and condensates and are being highlighted as very important for cell physiology. And together with that, the coacervate subcommunity is also claiming that could be a type of compartment that play a significant role in origins of life. So we will hear from Tony as well later on. So after this brief introduction into what the topics of the session will be, I will get into my own talk, which is going to be quite broad. But anyway, you have the papers there to go deeper into details, and as I said, I'm also available to discuss any other ideas or topic that you want to discuss with me. So my talk will be about the idea of minimal metabolism as a key concept to develop prebiotic systems chemistry. Okay, some years ago, together with Carlos Briones and Andres de la Escosura, we published this review on how some chemists, part of the community of organic chemists, and were synthetic organic chemists and supramolecular chemists as well, were becoming increasingly interested in exploring the complexity of some mixtures that could lead towards systems of biological or pre-biological relevance, and how this was providing us finally, at last, so to speak, with the right platform to actually approach the origins of life. Because the first thing and the starting point of all my talks typically is how complex. If chemistry is complex, then life is hyper complex. Okay, it's a hyper complex phenomenon. When you just think about what it means to have genetically instructed cellular metabolism with translation apparatus and all the rest of it, is just crazy. So the important thing is to realize how complex this is, and if it's that complex, the origins problem should also be aware of that complexity and take what we call a systems approach, which basically means that we have to take into account that previous ways of, when you are working on origins of life, of course you do simplifications, but previous simplifications, if we were trying to go to just one type of molecule, one type of chemistry maybe are too reductionist, and we have to be aware of that and maybe start with more complex mixtures as the general idea. Also, we have to realize that life has both an organizational and an evolutionary dimension, and they are actually get interwoven during the process of origins of life. I will maybe, if I have time at the end, I will say a few words about this as well. What we call the evolutionary cone and the organizational or individual autonomy perspective. Okay, and the whole process of origins of life, biogenesis, was an incredibly complex process itself. It took place in a long period of time, and in which many bottlenecks were present. And in order to overcome those bottlenecks, it's not something that you can do just taking an organizational perspective, even if it's just if this perspective, you can call it systems, because it relates to an organization of material components that they get together and they do things together, and even if you do have that approach, you're not going to be able to overcome those bottlenecks without having a different level of description and a different processes that take place at a different time scale, at a different space and time scale, which is the populational level, that will help you, not you, the systems involved, become increasingly complex as they go through those bottlenecks. So it's very important to have in mind that it's not only through an individualist proto-cell type of system that we're going to be able to understand everything. Instead, we have to envision a process like is depicted here in a recent paper that we wrote about these issues, more from a philosophical point of view, but also having a kind of a situation where initially you have a messy chemistry in messy populations of vesicles and protocells that are still very, very messy, with chemistries that are diverse and heterogeneous, and through various types of influences, environmental and also from the actual inherent dynamics of these vesicles, which could be fusing and dividing, but without much control initially. So a lot of stochastic behavior here, but progressively, as you go along, higher and higher levels of molecular and organizational complexity, you somehow take a subset of the chemistry of the molecules and the types of reactions that in principle organic chemistry would give you, which would be much wider than what biochemistry uses. And little by little, these very heterogeneous and messy populations would become more defined populations of different types of families here that would maybe engage in evolutionary dynamics, natural selection, competitive dynamics, also interactions that have to do with other types of maybe cooperation or proto-ecological webs here. And thanks to natural selection and other forces that, as I said, could be not just competition, but also cooperative forces, you would be reducing somehow the chemical diversity that you have at the beginning, but at the same time, you would be developing functional diversity, endogenous functional diversity. So somehow you start here at the bottom with a lot of exogenous driving forces, and little by little, the actual systems, by developing self-constructive capacities and metabolism and other types of mechanisms, they become increasingly complex, both from an organizational and molecular point of view, until eventually they could reach something like like the last universal common ancestor. Okay, all very speculative, but that's the general picture that we have in our heads. So so what we need is really a new generation of top-level researchers that have both analytical. The problem with systems, when you take systems approaches, is that you cannot forget about the reductionist approaches either. Okay, so you have to use both all the knowledge that we have from analytic and reductionist approaches, plus, so it's more work, let's say. So this new generation of researchers have to have both analytic and synthetic skills, and have truly a transdisciplinary spirit to push the field. Okay, so and do simplifications that are careful. Okay, with a set of hypotheses about what could be the relevant things, but don't simplify too much. Okay. The good news is that some of the seniors that are there in the field are becoming aware that, you know, one of the fundamental problems of origins of life, and maybe the hardest problem, is the origins of metabolism. And various groups in the world are trying this. There are different approaches. I think all of them are informative. Even sometimes there is a bit of tension between the different proponents of different hypotheses and settings for the origins of these proto-metabolic networks, from things that are quite far from biochemistry, like the hydrogen cyanide chemistry that Sutherland was developing some years ago, and showed us that some of the building blocks could come from that chemistry. Others that are much more like Joseph Morin's approach, that try to mimic more closely biochemical pathways without the intervention of enzymes, and showing that some of those pathways could run without the enzymes, which is very remarkable. Pauner's group as well, Markus Ralser, Ram and Greg's work, which we will hear about, which is kind of an intermediate between those two extremes. And then other people also from the systems chemistry community, like Ciprenoto's contributions, or this recent paper also by Grybowski's group, in which they starting from again organic chemistry, they propose some kind of bridge. The idea here is that the bridge between biochemistry and metabolic pathways and organic chemistry, which was not so evident, or the possibilities of having bridges between the two is being explored. And I think all of these approaches are welcome, and more people should be working on it. Still, there is the problem of what to call a proto-metabolism. Okay, what is a metabolism? What is a proto-metabolism? How do you distinguish that from just a reaction system? Okay, or a network of reactions coupled to some, you know, energy source like light or some other. How do you distinguish that from a real metabolism? And that my contribution is going to be on those lines in the context of a recent paper that I wrote together with Nino Lauber and Christoph Flamm. Nino Lauber is a PhD student that we co-supervise, Christoph and I. And basically we were trying to put together an idea of minimal metabolism that is in between chemistry and biology, because typically minimal metabolism is conceived as the metabolism related to the minimal genome or the minimal cell, like a Cray-Venter type of construct. And what kind of metabolism? Of course, this would be a genetically instructed metabolism with DNA, RNA, and proteins. But here, what we try to do is push the concept so that it helps the field of systems chemistry to actually envision some kind of connection with biological behavior, biological phenomena, and try to provide some criteria to say what is it that is special about the metabolism that is not just in a reaction network. Okay. So there are two sides of the story. I will go short because I don't have so much time, so you can go and read the paper. That is probably much better than listen to me today. But the idea here is that we need to go beyond the idea of self-organization, and we need to think about self-construction. So the idea of metabolism is self-constructing, and that has some cost. Okay, when you are working with molecules in the lab, sometimes it is also a message for synthetic biologists that take pieces of biomolecules and work with them as a kind of in a circuit or within a bioreactor in a vesicle. The actual part that has to do with the synthesis of those molecules is very important because it has a thermodynamic cost, it has an energetic cost. And nature, when there were no researchers picking up those molecules from real living beings and playing with them. It required an effort. Okay, so it's you generate an organization through synthesis, and synthesis involves this self-constructing effort. Okay, and the synthesis itself it takes place within an organization. Okay, so these are the two sides of the same two sides of the coin. Okay, and that involves also to have molecular control mechanisms on the processes of synthesis. Okay, and here we put the idea that those control mechanisms are the elementary functions. You could have kinetic control, you could have spatial control. So this is why I was saying when I mentioned Neil Delabay's work, the importance of having synthesis and at the same time, let's say, the formation of supramolecular structures or structures that can operate as rules or controllers on the synthetic pathways that you have in the system. So this is the key idea, and this is the fundamental figure that we have in the paper, in which we say that in order to be able to speak about the minimal metabolism, you need to distinguish two levels. One would be what typically people think about when they think about a metabolism, which is the reaction network with cycles or linear pathways, or a combination of the two. But it's very important to distinguish also that these synthesize some components that are going to be working as controllers of that system of reactions. Okay, so that you have the basic processes of transformation and reactions and all that, and then you have this level in which you have a combination of constraining mechanisms. And I think the most novel part of our approach is to say that this must be a truncated cone. Okay, so you cannot just think about enzymes, or you cannot think just about compartments, or you cannot think about other types of ingredients that could have control. But you need to think about a combination of that, a diversity of constraining mechanisms here. Okay, so that's so in a previous paper that I wrote with Carlos and Andres again, we were giving our hypothesis for which could be the minimal set of control mechanisms. Okay, some of them, the classical. So we could have catalyst, of course, for kinetic control. You could have compartments like vesicles, micelles for spatial control. You could have energetic control as well through coupling reagents here. Or you could also have, hereditary control as a kind of a minimum set of controls that could guide the system initially. And maybe you cannot shrink this tetrahedron farther than that, in the same way as you cannot, the truncated cone has to be kept as a truncated cone. Okay, so this is the type of graphical metaphors that we're using in order to show in which sense we cannot shrink and reduce things farther than to a limit. Maybe there is a minimal threshold that we cannot cross. Otherwise, we lose the essence of what biological phenomena could be, the starting point for biological phenomena. Okay, so I just mention a couple of work. Maybe you have heard about this from Sheriff yesterday. This type of approaches in which you are, you're having catalysts that also are coupled with membrane dynamics and stuff like that, are the type of approaches in which you have a diversity of constraints operating in the system, or Fletcher's approach, in which you also have, this kind of combination of processes and constraining structures in the system that with dynamics as well. So it's a mixture of things. Okay, so one of the take-home messages, more from a point of view of methodology, would be what is the pending task here. We really need to develop new techniques of analysis, both in vitro and in silico, to characterize non-equilibrium chemistries. We have to take seriously the non-equilibrium chemistry part, in the sense that we are traditionally synthetic chemistry and organic chemistry analyzes well whatever is in equilibrium, but we need, to have flow reactors and more work on that to be able to explore what happens far from equilibrium in these complex mixtures, and also analytical tools to tell whether these kind of molecular controls appear in the mixture in the same reacting pot, and what kind of effects they have on the reactions. That's the take-home message of our paper. Okay, I think I was also another part that is very important, and I'm involved in, is saying to what extent the heterogeneity of the medium where we carry out these reactions is important. And together with Peter Valde, we also wrote a review on how aqueous chemistry, but in the presence of soft interface-rich systems, like with the ones that you could have when you have lipidic domains or other types of systems, would be really the way to go, because you actually allow some chemistries that would not happen spontaneously in water solution to take place as well in the same system. And to finish, and I'm not sure how much time I have left, but well, just a couple of minutes, I hope. How am I doing, Uli? Just 1 minute. Okay, just so I finish with this idea, going back to the idea that even if we do this to start with a kind of a proto-metabolic or metabolic protocell, we will have, the challenge is huge, because we will have to go to a situation in which that proto-metabolic system would face all these transitions, and then we will have to deal with populations and dynamics of populations and all of that. But maybe I leave that for next, because Uli is getting a bit concerned about time, so I will leave that for a future contribution. Maybe the time when we, all of us, finally meet in person. I hope that it will be soon. So thanks a lot for your attention, and thanks again, Uli, for the organization, and for offering me this option to to record this in advance, because otherwise I will be dead in the middle of the night. So as I said, okay, all the best, take care, and see you soon, I hope. Just the last slide that I forgot to show at the end of my talk, which is just to thank you, my PhD students, which are the heart of my activity as a researcher, and in particular also the collaboration with Christoph Flamm here from University of Vienna in this paper that we just published. So thanks again.